Good morning, LS&GS student. This is your math teacher, Ms. Yuval. Our lesson today is about also lines and planes. In fact, this is an exercise with the required solution. But first of all, we are going to read this question. In the plane of a direct orthonormal system OIJK, consider the three planes P, Q, and R of equations 2x, the plane P of equation 2x plus y minus 2z plus 1 equal to 0, q x plus 2y plus 2z minus 1 equals 0, and r equal x, or its equation is x minus y minus 4z plus 2 equals 0. And we have the straight line D here of parametric equations x equal to m plus 3, y equal m, and z equal minus 2m minus 1, where m belongs to r. Our first question is, in fact, they ask us to prove that the three planes intersect along a straight line L of parametric equations x equal 2t minus 1, y equal minus 2t plus 1, and z equal t, where t belongs to r. If I'm going to prove that planes are intersect along a straight line, first of all, I'm going to prove that they are not parallel or confounded. So I'm going to take the equations of the planes 2x plus y minus 2z plus c. I take u over u, v over v. They are not equal, then the two planes are not parallel, so they are intersecting. Similarly about plane P and R, similarly about plane Q and R. So we can take u over u not equal to v over v, then we can deduce that the three planes are not parallel to each other, or they are not confounded. In fact, they are intersecting. Now, we need to prove that the straight line lies in the three planes. So I'm going to substitute or to replace the parametric equations of the required straight lines and the Cartesian equation of each plane. So in P, I notice that for if we replace the parametric equations of the straight line L in P, we obtain 0, so I can deduce in this case that L is a subset of P, also L is a subset of Q, also L is a subset of R, so I can deduce that the three planes intersect along the straight line L. In the second question, they ask us to verify that D and L are perpendicular at a given point E. So I prefer first of all to start by proving that E belongs to both straight lines, or the two straight lines intersect at a point E. I prefer here to use for m equal minus 1 in the parametric equations of the straight line D, if we replace m minus 1, we obtain x equal 1, y equal negative 1, and z equal 1. So I can deduce in this case that E belongs to the straight line D. If I can use t equal 1 here, I notice that x equal minus 1, y equal minus 1, and z equal 1. So I can deduce that also E belongs to the straight line L. Then the two straight lines are intersecting. Now what I'm going to do, I can determine the director vector of the first straight line D, which is 2, 1, and minus 2, and the director vector of the second straight line L, 2, minus 2, and 1. To prove that these two straight lines are perpendicular, of course, first of all, we prove that they are intersecting. I can take the scalar product of their vector product. It will be equal to 0, then these two vectors are orthogonal, so I can deduce that the two straight lines are perpendicular at the point E. In the second question, they ask us to find a parametric equation of the bisector D of one of the two angles formed, of the angles, in fact, formed by D and L. We notice that the modulus of the director vector of the straight line D equal the modulus of the director vector of the straight line L. And we can use this property. In fact, if I have a parallelogram with this side and this side have the same modulus, then this is a rhombus. So by using the parallelogram rule, the director vector of this line, it will be the sum of these two vectors. So if this is W, the vector W, I can say that the vector W equal U plus V using parallelogram rule. So, and this is the bisector of this of the angle formed by these two vectors, in fact. So I can use the director vector. I can determine the director vector of the bisector by using S of t plus S of L, which gives us 4 minus 1 and minus 1. And this line, of course, passing through the point E. So the parametric equations of the straight line D are x equal 4n plus 1, y equal minus n minus 1, and z equal minus n plus 1. Now they ask us to determine the angle between the plane R and P and the plane R and Q. They ask us to determine cosine alpha and cosine of beta. Then we can deduce the value of alpha and beta. Then also they ask us to prove that P and Q are perpendicular and that R is the plane of the dihedral PQ. First of all, now I can determine the normal vector of the first vector, the normal vector of the second vector. We know the normal vector of the first plane, the normal vector of the second plane. By the way, remember that the angle between two planes, cosine alpha of the angle between the two planes equal the scalar product of the normal vectors of these two planes over the norm of the product of the norm of the two normal vectors. Then we can deduce that, and R dot n. Since they ask us about acute angle, I put here absolute value. So we obtain radical 2 over 2, and we know that if cosine of alpha equal radical 2 over 2, then the angle equal 45 degrees. We are talking about an acute angle. Similarly, cosine of beta equal radical 2 over 2, then beta equal 45 degrees. Since alpha plus beta equal 90 degrees and alpha equal beta, this leads that P is perpendicular to Q, and that R is the bisector plane of the dihedral PQ. The last part here, part 4, let A be the point of intersection of R with the abscissa axis. Since the point is on the abscissa axis, then its ordinate and its elevation are equal to 0. So A belongs to x prime x, then y of A equals z of A equals 0. And A belongs to the plane R, so I can replace the coordinates of A in the equation of the plane R, so we obtain x of A equal minus 2. Then the coordinates of the point A becomes minus 2, 0, or in fact they are minus 2, 0, and 0. The distance from A to P we use, and they ask us also find the coordinates of A and calculate its distance to plane P. By using the formula 2x ux of A plus Vy of A plus Wz of A plus R over the modulus of the normal vector, we obtain the distance equal 1 unit of length. Then they ask us to deduce the distance from A to the first to Q. Of course, since A is in the plane R, then the distance from A to R is the same as the distance from A to Q, since any point on the bisector plane is equidistant from the other two planes. So I can deduce that the distance from R to Q is also 1. Now they ask us to determine the distance from A to the line of intersection. I have here the form of a square, or in fact a square. So this one be as a right triangle. So I can deduce that d square of A L, the distance square from A to L, equal to the distance square from A to the first plane plus the distance square from A to the second plane, which is 1 plus 1 equal 2. Then the distance equal radical of 2. Now P prime and Q prime are two planes passing through the point A and parallel to P and Q respectively. They ask us to prove that the straight line of intersection L prime and of P prime and Q prime is parallel to L. In fact, since P prime parallel to P and Q prime parallel to Q, and A is a common between P prime and Q prime, then we can use that L prime is parallel to L. This is a property from the last year, from the second secondary. Or simply we can determine the equation of the plane P prime, the equation of the plane Q prime. We can determine the system of parametric equations of their line of intersection, and we can deduce in this case that their director vector are collinear, so they are parallel to each other. This is all for today. Thank you.